you for the introduction and good afternoon. In principle, this talk belongs more to the test case session because, yes, as you said, I want to present an exact analytical solution for the compressible Euler equations. The talk is divided into two parts. The first part is a description of the analytical solution itself, and the second part is simulations with the icon model, which were performed by my colleagues Daniel Reinert and Günther Zengel, who are one of the main developers of the icon model. Motivation, yeah, we all know that for the development of dynamical cores or numerical methods in general, it's to have idealized test cases is the most important evaluation tool for us. What are the requirements of such idealized tests? Yes, of course, they should test the model in a mode which is relevant for the application of the mode, so in the parameter space which is relevant for this model application. The second is the idealized test case should be implemented not too difficult, should be easy implemented, and another relevant issue is, of course, that the solution of this idealized test case is reliable. And yeah, one way to get reliable solutions is, of course, to have analytic solutions, and you know that there are several analytic solutions available. So, for example, stationary flow over mountains, we have several linear solutions available in the literature. There's also this famous solution by Long for nonlinear solutions of flow over mountains. Here he derived it for Boussinesq approximated atmosphere. We have also on the sphere several solutions here, for example, a paper by Staniforth and White for balanced stationary solutions on the sphere. And actually, the starting point for this work here was a paper by Bill Skammerog and Joe Klemp, which defined a very well-known test case, namely the expansion of a weak warm bubble in a 2D channel, and this bubble generates gravity waves which expands. And in this paper they also gave an analytic solution of this problem for a Boussinesq approximated atmosphere. But one must say that most of the other idealized test cases which are used normally only possess known solutions which are gained by other numerical models. And it's even more rare that analytic solutions use exactly the same equations than the model under consideration. So in the sense that the model really converges to this analytic solution. And I hope I can give you one example of such an solution where the model converges to. So let's start with the non-hydrostatic compressible Euler equations. Here the three equations for the velocity containing optionally an Coriolis force term. Compressible equations, this means the continuity equation for density, and here in this also an equation for pressure for adiabatic flows. This test case consists on a flow also in a channel, on a spherical channel, let's say. So the boundary conditions are free slip conditions on the surface of this sphere and a free slip condition in a height h above the surface of the sphere. So most global models which use the compressible equations should be able to exactly use these equations in the dynamical core. It is important to apply the shallow atmosphere approximation for the derivation of this analytic solution, and also one further approximation, this is linearization. And like all the perturbation techniques, linearization is a controlled approximation. If you think, okay, my perturbation is too strong, I reduce the perturbation, then all the higher order terms are vanishing. So linearization is a quite good approximation. The linearization took place around an isothermal state, a steady atmosphere and a hydrostatic atmosphere. It can be either at rest or it can have a constant background flow. Some words about the solution strategy. One important point is really that the background state is isothermal because in addition with a shallow atmosphere approximation, by a Bretherton transformation you can transform the PDE system in a system which has only constant coefficients. All the coefficients are constant. And therefore, by a spectral representation of all the fields, this PDE system is solvable. So spectral representation in the vertical by a Fourier decomposition, and in the horizontal directions by decomposition into spherical harmonics. And at the end, the time integration takes place by a Laplace transformation. I said important point is the shallow atmosphere approximation. It means replace all prefactors 1 divided by r by 1 divided by the Earth's radius. So hopefully your global model, if you want to use this test, is able to use this replacement. The second is the divergence operator. Here one should be able to omit the metric correction terms, which is proportional to the vertical velocity divided by r. This is also a shallow atmosphere approximation. But apart from that, all other Earth curvature metric terms are included in this analytic solution. If you optionally want to use Coriolis force, that's a little bit a special point, because to derive the analytic solution, it means that the angular velocity vector must have a special form, namely it must be in every point on the sphere, it must be proportional to the radial basis vector multiplied by a constant. It's really a constant, it's not any dependency of the latitude. This sounds a little bit strange. Obviously, there's no planet in the whole universe which has such a Coriolis force, but it allows the analytic solution, and it's quite easy to implement in the model. So in the icon model, it was really the replacement by one code of by one. So it's easy to use. So how looks the analytic solution like? This is here, for example, the vertical velocity, or better say, the component with vertical wave number kz and spherical harmonic with indices L and M. You see it's proportional to the density at the initial time, and the whole time behavior is described by this expression in this square brackets here. You recognize that there occur two frequencies, alpha and beta, and they are simply determined by the dispersion relation of the expansion of gravity and sound waves in this spherical shell. So recognize here the beta, the acoustic wave branch, and alpha is a gravity wave branch. So which categories of tests can be performed? The first is only to have gravity wave and sound wave expansion, of course. The second one is described by the formula I just showed. The second one is you can additionally superpose advection by a solid body rotation velocity field. So by this one. This is also an important test because in every split explicit or in semi-implicit codes you have a splitting between the slow modes, the advection normally, and the fast mode. So this is also an important test. The third category of test is to add the Coriolis force, is a little bit strange, globally on a local f-plane. So it's really a local f-plane approximation. So in a vicinity of a certain point, you have this local f-plane approximation. So it's not such a bad test. So you should be able to test the proper discretization of inertial gravity wave modes. And we know from talks from Monday and also from talks at the last PDEs that this is not a simple problem, because one knows from the paper of Niskovich et al. That the secret discretization on non-quadrilateral grids can be difficult, especially on hexagonal grids. And now since a couple of years we know the solution by the papers of Subern, Ringer, Skaborg, and Klemp and Gassmann, how to deal with such problems on the C grid. So with this test one should also be able to test it. So how to initialize the test? It's not so difficult because the initialization is quite similar to a test case which was used by the DCMIP test of this year. So it consists of the initialization of temperature fields. In the vertical mainly it's a sinusoidal form of the temperature perturbation. It's modified a little bit by this exponential factor, so you have a little bit an asymmetric form in the vertical, but this helps in the calculation of the analytic solution. And in the horizontal directions, you can choose an arbitrary function. Here I've choose this function here because this form of the horizontal dependency has a finite expansion into Legendre polynomials, which also helps. You should use a quite weak bubble, so you are in the linear regime. It's reasonable to perform a small Earth simulation. The idea of small Earth, I think it was first came up by the paper of Nils Wedi and Piotr Smolakiewicz. Here it means we have chosen a sphere which has radius, Earth radius divided by 50, so you end up with such a small sphere here. It means that if you make simulations with a reasonable resolution, so let's say 1 degree up to 1.5 degrees, you end up with these grid sizes, so it means you are in the non-hydrostatic regime. And if for instance with Coriolis force, we multiply the Coriolis constant with a factor of 10, so it means overall the Rossby number is changed a little bit, but it's changed not too much. And also the ratio between this Coriolis constant and Brand-Weisler frequency is increased, so the influence of the inertia effects on the dispersion relation are a little bit enhanced compared to the buoyancy effects. As I said, simulations are performed with the ICON model. ICON stands for icosahedral non-hydrostatic. It's a joint development of the Deutsche Wetterdienst and the Max Planck Institute for Meteorology. Tomorrow you will also hear some talks by Günter Zengel and Florian Prill about this, and there are also posters by Pilar Ripodas and Daniel Reinert. So only some words. So ICON also uses secret discretization, in this case on a triangular grid decomposition of the icosahedron. It's mainly a mixture of finite difference and finite volume discretization, and the time integration is mainly a predictor corrector scheme. So here you see the initialization of this test case. Here the warm bubble starts and the gravity waves expand over the sphere and are going back. So it's perhaps more intuitive to look at a vertical cross-section. Here you have on this, here the North Pole, equator and South Pole, and here the vertical direction. On the upper part you see the simulation without Coriolis force, and in the lower part with Coriolis force. And in all the pictures you see now, the black lines, black solid lines are the analytic solution, and the colors denote the ICON simulation. So this is the initial state. After 15 minutes you see the expansion of gravity waves from this warm bubble, and then after half an hour you see first differences in the solution with Coriolis force. What is well known result that at the initial area this warm bubble remains, and the expansion of gravity waves is a little bit weaker in the case with Coriolis force. Then gravity waves expand over the equator, are going to the southern hemisphere, and after 19 minutes, here you see some differences between the analytic solution and the ICON simulation here and here. This was a simulation with a quite high resolution of about 0.1 degrees. It's also intuitive to look to the convergence of the model. So now we have chosen a quite coarse resolution of its nomenclature of ICON R2B4, roughly 1 degrees of resolution. Here you see now that there are some differences between the ICON simulation and the analytic solution for temperature. If we increase the resolution here to 0.5 degrees, you see, okay, ICON model converges really to this analytic solution. Now if I go back and we look to the vertical velocity, you see, oh, what's happening here? The differences between simulation and the analytic solution are much bigger, but again we have a convergence. If I increase the resolution, then the model has some convergence. So the convergence rate of the ICON model, here you see on the left picture the temperature errors. an infinity and L2 error. In fact, you see 4 lines because also the results for runs with correlate force and without correlate force are plotted here, but the curves with correlate force are almost the same than without correlate force. So obviously the Icon model has no problems in the simulation of inertial gravity waves. What we see also is that the convergence rate, as we have seen just before, the convergence rate for the vertical velocity is, okay, the rate is the same, but the errors are much bigger than the errors for the temperature. The overall convergence order for Icon is, as you see here with this line, is first order. You must think that it is the convergence for a spatial and temporal problem. Some remarks about this vertical field simulation. You have seen, okay, the convergence is a little bit, it's not so good as for the temperature. This has some reasons, and to improve this a little bit, you have first to think about the time step, delta t. So it's a compressible solution, so you must be able to simulate also the sound waves in a proper way. This means your time step must be chosen that sound waves are resolved, really resolved, even if you have a semi-implicit time integration scheme. For the small Earth simulations, this is perhaps not such a problem because the horizontal and vertical grid mesh sizes are of the same order. This should be okay. If you want to simulate the real Earth, then normally the horizontal grid sizes are much bigger than the vertical ones. And so you have some additional limitations, and you should also keep in mind that delta t is additionally limited by the acoustic cutoff frequency of at least 1 minute. So the general message is delta t is not only limited by stability, as it is normally chosen in your model, but also by accuracy, so by these sound waves. A second aspect is you may say, oh, we are not interested in sound waves, nice thing, but we want to damp them. Here in these tests, we have to reduce the off-centering of the sound wave propagation. So the Icon model also uses a horizontal explicit, vertical implicit time integration scheme, so we can pick out the off-centering for the sound waves, and this is really reduced to a minimum. For the Icon simulation, it was the off-centering was 0.01. Similar simulations with our regional Cosmo model we were able to run the model without any off-centering for sound waves, and this really helps in these sort of simulations. What about other damping schemes like divergence damping? So we found this is not really a problem. So divergence damping is used normally in split explicit schemes to stabilize the whole time integration scheme. And this is not a problem because the divergence damping factor should go to 0 in the convergence region. And so it's, for example, in the paper of Skamrock and Clamp, it was recommended to choose this alpha, this constant proportional to the time step, and this vanishes simply if you are converging. Okay, last slide, a summary. So an analytic solution of the compressible non-hydrostatic Euler equations on the sphere was derived. That means that now you have a reliable solution of a very well-known test case, and this can be used not only for qualitative comparisons, but really for convergence tests, as I have shown you. This test setup is quite similar to one of the DCMIP test cases, so it shouldn't be too difficult if you took part in this modern comparison workshop to do this test. Standard approximations are used, so this globally local F-plane, which is not too difficult to implement, and also this shallow atmosphere, which is perhaps a little bit more difficult. Only one further approximation was used, the linearization, also not a problem. And as I've shown you, for fine enough resolutions, the Icon has a spatial temporal convergence rate of about 1, and we didn't see any drawbacks. So these are quite new results. No publication is available, but at least for a similar solution on the plane 2D channel, there is now a paper submitted to the quarterly journal. So thank you very much for your attention.
Questions? Do you think that this technique could be used to make analytical solutions for the problem of flow past mountains on the sphere?
Okay, yes. In principle, it's same solution strategy. Yes, and the main idea was here really to have a solution which is very close to the equations of the model, and also the solution which is unstationary in time, so you can test both your spatial and your temporal discretization. But I think the solution strategy is similar.
So many of models use a flux form, and your test is based on advantage for a waveform.
Yes, but
do you expect this test will be in favor of adaptive form than a flux form?
But this shouldn't be a problem because for the analytic solution, so there are no shocks and other discontinuities. So it's.
Yeah. But in a discretized world,
yes, but
the flux form introduce extra terms compared to the adaptive form. That's why I'm just wondering.
This shouldn't be a problem, I think. And as I said, the icon model is a mixture of a finite difference, finite volume, discretization, and it works.
For the scalar thermodynamic variables, it has a flux from discretization.
Yeah.
Any more questions?
I think to make the ratio f over n more Earth-like, you could just change the g. And then you have the full Earth-like kind of run.
Yes, that's right. So when we choose these factors, we actually looked at the pictures and we wanted to see, okay, some influence of the Coriolis force, so some differences to the runs without Coriolis force. And on the other hand, not so strong influence of the Coriolis force. That's the reason why we have chosen these values. And one can discuss about this, obviously, yes. Perhaps not too unreasonable.
Do you think you can overlay a background flow on top?
Yes. We didn't do this yet because this overlay is a little bit tricky. Probably the problem with the icon model is to have a divergence-free background flow. This is why I didn't show yet such results. But as I said, this is this second category of tests. I think it's quite important to do this test with a solid body rotation background flow. Yeah.
Any more questions? That's the case, then let's thanks Victor again.